Good morning. We will continue. So we were discussing about what are the differences between real cycles and ideal cycles. Ideal cycles we have studied 8 cycles, and then one by one we are accounting for all the differences. Basically, what we are seeing is how to incorporate these differences into our calculation so that we can take the variations that occur in real cycle. So what we have seen till now, first we have seen how to take into account the change of kinetic energy. Then secondly, we have seen the most important part, how to take into account the fact that the compressor and the uh, turbine expansion process, compression process and the turbine expansion processes are non-isentropic, means they have losses. Then we have seen briefly how to take pressure losses into account, pressure losses in the occur in the regenerator and also in the combustion chamber. And we have also seen how to incorporate the fact that the regenerator also is not 100% effective using a regenerator effectiveness parameter. A few more things are need like we need to discuss. So the next point is variation of the gas properties. So for ideal cycles, we generally assume that the working fluid is air. Okay. So if there is a problem, say in your exam or in an assignment, where it is mentioned that there is an ideal cycle and it is not mentioned what is the working fluid, you should take air as the working fluid with the air properties. So air properties you should always know. Means uh, like you should not expect that it is given. Means Cp and Cv and gamma and R of air should be known to everyone. It is used in all different courses and in real life also it is required. Yes, so Cp generally we take as 1.005 or 1.004 kilojoule per kg Kelvin. Gamma is 1.4 and R is 0.287 kilojoule per kg Kelvin, 287 joule per kg Kelvin. And Cp minus Cv is equal to R and Cp by Cv is equal to gamma, right? So this gamma is important for calculating all the temperature and pressure relations, right? Because if it is an isentropic process or even non-isentropic process also, first to calculate the isentropic part, we need the value of gamma. And Cp has a very important role to play because Cp uh, dictates how much work is required or how much work is generated by the turbine, how much work is required by the compressor or how much work is generated by the turbine for a given temperature difference. Okay, so even in means I mean that not only in the calculations in real life, Cp will dictate means how much heat is per unit temperature change, how much heat is required, how much energy is required. That is dictated by Cp, right? So we know that Cp is a function of temperature for gases. Cp generally increases with temperature, and is a very weak function of pressure. So generally it is ignored that it's also a function of pressure. It's a very weak function of pressure. So, but in our cases, not only we have to consider that Cp is variable due to temperature, but also what is happening is that the composition varies. So the initial composition is that of air. Intake composition is of air, and then in the compressor also we have air, and then in the combustion chamber during the combustion the composition changes. So what are the combustion products? Everybody knows. For a hydrocarbon, the combustion products. If there is complete combustion, the combustion products are carbon dioxide and water vapor. But in this case, because we have a very large excess amount of air, there will be a large amount of oxygen and nitrogen still present. Means a large amount of air still will be present, plus the newly formed water vapor and carbon dioxide. So as a result, because of this change in composition of the gases, now it's a mixture, so it's complex it's complicated to calculate these values. But what will happen is that the Cp and gamma values will change. Okay. So we can see that here. So gamma is Cp by Cv by definition, and gamma minus 1 by gamma, which is equal to 1 minus 1 by gamma. Gamma minus 1 by gamma is the factor that we always use, right? Just a second, please. Okay, so gamma minus 1 by gamma, which is 1 minus 1 by gamma, which is equal to 1 minus Cv by Cp. It's not read to. I don't know why I have done like this. So Cp minus, okay, I understand. So Cp minus Cv by Cp, which is R by Cp, is equal to universal gas constant R bar by M. R is universal gas constant by M. Okay, M is the molar mass of the gas by Cp. So because the composition is changing, the molar mass is changing. Cp also is changing. So the term gamma minus 1 by gamma also changes. Okay. So gamma and Cp is a function of composition and temperature. And it is not easy to calculate. So obviously, if you are working in an organization which works on the design of say combustion chamber and the turbine. So basically, which works on the design of a gas turbine engine or jet engine. Say you are working in Rolls Royce or you are working in uh, Pratt and Whitney or you are working in GE. So in those cases, there will be much more detailed analysis to calculate these values exactly. Okay. But for our courses, we will take a very quick and dirty approximation, means a very quick approximation. So we will just take that for the part up to the combustion chamber, up to the inlet of the combustion chamber, which is generally air. We will take the air properties. Cp is equal to 1.005 kilojoule per kg Kelvin and gamma is 1.4. So all the calculations regarding compressor. Later on for the jet engines, we will also have a diffuser in front of the compressor. So for the diffuser and inlet of the combustion chamber, these are the properties that we are going to use. From the exit of the combustion chamber and the turbine, and later on when we study about jet engines, we also have to calculate for nozzles, convergent nozzles, convergent divergent nozzles. So in those cases, all cases, we will take an approximate value of Cp empirically determined, which is equal to 1.148 kilojoule per kg Kelvin, and the gamma value we will take to be equal to 1.333. Okay, so these are approximate values, and for the simple calculations, this work well. These are empirically taken. Okay, and in real life, obviously, it is much more complicated. So what happens is that even if we do ideal gas and means ideal cycle analysis with constant value of Cp 1.005 and gamma 1.4, because they act in the opposite direction. So Cp actually is increasing after the combustion, whereas the gamma decreases. If you see the equations in like the effect, net effect, you will see that because they vary in the opposite direction, their effect is somewhat means cancelled. So it is not a cumulative effect. The overall effect is somewhat less than the individual effect. So that's why even the ideal cycle calculations are quite accurate. But when we go for real cycle, means real calculations, if we take these approximations, it will be much more accurate. For even better accuracy, what needs to be done is that we need to write programs where, say, with a certain value of Cp, say you are starting, so Cp is a function of temperature and composition, okay, and we are starting with a certain value of composition and temperature, and we find we use a particular value of Cp. Then we find that this is the temperature rise that is occurring. based on that that value of Cp and gamma. Then for this new temperature rise, we will have to, like for a time step, we will have to iteratively calculate. So we will have to calculate what will be the new value of Cp and gamma, and then use it for again calculating the temperature. So it will go on like a iterative process until convergence. Obviously, that is beyond the scope of this course. But if you do actual design work in any of the organizations, then you will need to write programs actually, or use some tools, in-house tools to do this type of calculations. So to summarize this part, basically for all the parts up to the combustion chamber inlet, these are the values that we are going to take. Cp equal to 1.005 kilojoule per kg Kelvin and gamma is equal to 1.4. And from the combustion chamber outlet, turbine and nozzle, all these parts, we will take Cp as 1.148 kilojoule per kg Kelvin and gamma as 1.333 for real cycles. For ideal cycles, obviously, we will continue with the. If it is mentioned that it's ideal cycle, we will have to do ideal cycle calculations to simplify things. So next point is the effect of mechanical losses. Mechanical losses are friction losses that occur. The other friction losses, the losses like there are frictional losses which leads to pressure drop, which we have already seen, and then there are frictional losses, viscous losses, which leads to the non-isentropic processes in the compressor and turbine. That also we have seen. There are other frictional losses. One occurs because there are frictions between. So one, we have a rotating shaft. So there is a rotating part which is mounted on a fixed part. So this is mounted using bearings, right? So there will be bearing friction, very less amount of friction. These are very well lubricated, and so very less amount of friction will be there. And then there is something called windage friction, windage losses. Okay, so you have some static amount of gases at the edges, like between the casing and the blades, or between the diaphragm, basically, and your moving part has to cut through it. So that also results in some frictional losses. So overall, the effect is about 1% approximately. Obviously, it can be 0.8%, 1.2%, but typically it is like the approximate value is about 1% of the compressor work input. So this how we incorporate in the calculation. We incorporate by defining a new efficiency, which we call as transmission efficiency. Remember that the turbine and the compressors are mounted on the same shaft, right? So the turbine, when it is rotating the shaft along with it, and this shaft is rotating the compressor. So the power transfer is direct from the turbine to the compressor, directly through the shaft. Okay. So because of friction, what is happening is that if a certain amount, say if 100 kilowatt of power is required for running the compressor, because of friction, the turbine needs to supply a little more amount of work for running the compressor. So that little more amount, what is the value? That is incorporated by defining this transmission efficiency. Okay. So if the compressor work input in ideal cycle is Cp into T02 minus T01, for a real cycle, this compressor work input will be equal to Cp delta T and Cp T02 minus T01 into 1 by transmission efficiency. So if transmission efficiency is 99%, so you will need this value, ideal cycle value, divided by 0.99. So around 1% increase of work will be required. So this is the amount of work that is required to be obtained from the turbine to run the compressor. So when we calculate the turbine work, say turbine is generating 200 kilowatt of work. And in an ideal cycle, we were seeing that the compressor requires 100 kilowatt of work. But now we will have to calculate the compressor work as 100 kilowatt divided by 0.99. So it may be 101.11 or something like that. So, and 101.01, something like that. And then you have to subtract this from the turbine work output to get the net work output. So instead of 100 kilowatt net work output, we will be getting something like 89.99, 98.99 or something like that kilowatt. Okay. So this is how we take this into account. There are other minor losses because of additional equipment, okay, such as you have to run the fuel pump, oil pump. Oil means lubricant. Okay. Lubricant pump, fuel pump. So all this we need to run. So those also take some amount of power. Okay. So if we can consider all this together, minor changes, or we can ignore even this in our calculations for these auxiliary equipments. So the next variation from the ideal cycle. So, any questions? The next variation from the ideal cycle is that the mass flow rate does not remain constant. Till now, we have considered that the mass flow rate is the intake mass flow rate m dot a. M dot a is the mass flow rate of air. What happens is that this is the mass flow rate till the inlet of the combustion chamber. But in the combustion chamber, we are also injecting fuel, and the fuel has a certain mass flow rate. Let us call this as m dot f. Okay. So a fuel air ratio can be defined m dot f by m dot a. Typically, what is the value? I have already explained previously. What are the typical values of fuel air ratio that is used in gas turbines? Any approximate values? Can you tell? Why everyone is silent? Because it's early class, huh? Just switch on and then sleep. Yes? 1 is to 50.
50, sir.
Typically around that. Okay. Up to is not correct because we will not have very small values. Like you will not have near stoichiometric values. So maybe 1 is to 40, 1 is to 50 like this. So it means that the mass flow rate of fuel is very small as compared to the mass flow rate of air. Okay. So the increase in mass flow rate, which can be taken into account like this m dot a plus m dot f. The new mass flow rate will become m dot a plus m dot f, which is nothing but equal to 1 plus f into m dot a. So this new mass flow rate is written as m dot g. Okay, these are standard symbols. Don't use arbitrary symbols. Okay, don't use m dot 1, m dot 2, something like that. Use the standard symbols because these are, then everybody understands what is the meaning of this. So m dot g is equal to 1 plus f m dot a. So around 2% increase of mass will occur, mass flow rate will occur because of injection of fuel. Now there is also bleeding of air, which I have not shown here, but it was written here, so that's why no one was answering. So there is also bleeding of air. Bleeding means that some air is taken out. Some relatively cold air is taken out. Now, why I am telling relatively cold? Because actually it is taken out after the compression, after the compressor has compressed the air. So after compression, the temperature increases because of the compression process. Temperature may be around 500 Kelvin or something like that. Okay, we have seen a problem also. I don't remember what was the value after the compression, but some value would have been there around 500 or 600 or 400 something. So it is not actually cold air. It's quite hot, more than 100 degrees centigrade, 150 to 200 degrees. This is used for cooling. This air is taken out, and this does not take part directly in the combustion process. So this air is used for cooling the turbine and the turbine blades basically. And the cooling of the combustion chamber, that is done separately. The part of the air which goes for combustion, that is introduced little by little. At first, only a small amount is introduced, like a stoichiometric amount, so that the primary combustion can occur properly. Then some more amount of air is introduced from the sides, which is known as secondary air. Okay, then some cooling air is introduced. So all this mixed together to give rise to the combustion products. That is different, and this bleed air is different. This bleed air is taken out after the compressor and used for cooling the turbine blades. And as I already mentioned, very high amount of air fuel ratio is maintained so that the maximum temperature is lower. It's a very common question asked in the interviews if you go for this type of jobs. Okay, why the air fuel ratio is kept high? It is not anything related to combustion process. It means it is related obviously to combustion, but it's not for maintaining combustion or anything. It is for keeping the maximum temperature lower. Because we have to always think from practical point of view what is happening. If you are developing a gas turbine for a jet engine, so basically you have to think what are the most costly equipment or most costly part. So most costly part are the turbine blades, which are created using single crystals and directional solidification. So it is very important that all the other design also works around that. So generally students ask a question here sometimes, but because you guys are not asking, I'm going to ask you that this air which is taken for cooling, we are taking after the compressor, and it has become somewhat hot, right? 200 degrees centigrade maybe. So why I'm not using the direct air from the inlet? Because it will be much colder, much cooler. Say around room temperature, or if it is a aerospace engine, jet engine, it will be even lower in like sub-zero temperature. So I am not using that air for cooling the turbine blades.
So pressure is very low, so density is not going to be very high for the inlet air.
It was started correctly your answer, but then it did not finish. That is not the cause. Okay.
So,
So yes.
so
After
the
a
stagnation.
compression, pressure will be same as the air which is coming out of the combustion.
Correct, correct. So pressure. So actually, yes, Nikhilesh's answer also started correctly. Pressure is high pressure is required, because otherwise, how will you inject the air into the turbine part, right? Backflow will occur. If you have to inject some cooling air, that has to come at a pressure which is equal or higher than the pressure that is existing in the turbine. Okay, so because that air will be mixing with the turbine gases. So if you have a lower pressure inlet, actually the combustion products will flow in the opposite direction. So that's why you need high pressure air for cooling, and you need to use the air which is coming from the compressor. Is it clear?
Yes, sir.
So the final point is effect of the fact that the combustion process is not 100% efficient. But remember that combustion is very efficient in gas turbines. Okay, it is very close to 100%. Unlike other IC engines that you study, where the combustion efficiency will be much lower. In these cases, this is very high, around 98%, more than 98%, because you have very high air fuel ratio. Okay, so there is lot of availability of oxygen for the combustion to occur, and as a result, the efficiency is very high. And there is also a lot of uh, say what is it? Lot of driving force to make the efficiency higher. So if you design a car, right? If you design a car, also we want a very high efficiency car. So say I was looking for a new scooter yesterday. So I was also looking at what is the mileage that we obtain. So we want good efficiency, but it is not as important as the efficiency of a gas turbine, because you have to carry the fuel, particularly for jet engines. You have to carry the fuel with you, and even small increase in weight of the fuel leads to much higher cost of operation, right? So you want the gas turbines to be much more efficient. So you want to you are ready to put more money for doing more experiments and calculations, so that you can increase the efficiency of combustion. As a result, the combustion efficiency is very high in gas turbines. So how this is accounted for in our calculations? This is accounted for by defining a parameter which is known as combustion efficiency. Okay, eta B, burning efficiency or combustion efficiency. We'll call it as combustion efficiency. So this is equal to the energy rise that is occurring in the combustion products. So what is the energy rise in the combustion products? So at the outlet of the combustion chamber, the enthalpy is equal to So mass flow rate is equal to 1. So we will calculate per unit mass flow rate. So per unit mass flow rate at the inlet, the mass flow rate at the outlet of the combustion chamber is 1 plus F. So our base is the inlet mass flow rate in the gas turbine, m dot A. Okay. So all the calculations are done in terms of unit inlet mass flow rate. Okay. So the mass flow rate through the turbine and after the combustion chamber is equal to 1 plus fuel air ratio. So it will be around 1.02, something like that, into CPO of gas. Okay, what is the value we have just seen today? 1.148. Okay, into T03. T03 is the maximum temperature, turbine inlet temperature. So this is the outlet temperature from the combustion chamber. So this is the enthalpy per unit mass flow rate at the exit of the combustion chamber. Per unit mass flow rate means per unit mass flow rate at the intake. Okay, minus the enthalpy which comes into the combustion chamber, which is 1, mass flow rate is 1 at the inlet per unit mass flow rate. Okay, 1 into Cp of air into T02 inlet temperature. This is the compressor outlet temperature, combustion chamber inlet temperature. So this is the rise of change of energy, increase of energy in the combustion products. This divided by the amount of chemical energy that is present available for combustion after combustion. Okay, the calorific value of the fuel QCV into the amount of fuel. So per unit mass flow rate of air, the amount of fuel is equal to F. So in means if you do in the dimensional terms, the amount of fuel is m dot F. Per unit mass flow rate, it is m dot F by m dot A. So it is equal to F. So F into QCV. So typically this value is around 98%. So this is how we will do the calculations. From here, we can easily calculate. Either if we want to calculate fuel air ratio, if we know T03 and T02, we will calculate the fuel air ratio from here. If on the other hand, fuel air ratio is known, T03 can be calculated. Typically, what values will be known here after like for doing during this calculation? What are the known values that you expect? What are the values that you expect to know here at this point of calculation? So generally, when we start calculating, we start from the intake, combustion process, intake, compressor process, combustion process, turbine, nozzle, like this. Okay. So in this case, nozzle is not there because we are studying in industrial turbine. So in these cases, compressor, combustion chamber, turbine, like this we go. So at this point of calculation, when you come to the combustion chamber, what are the known values? And using this equation, what unknown can be obtained? Among all the parameters. Quickly. I want quick answers because we are going late today.
T02 can be known.
T02 is known because we have already calculated it using compressor process, right? Correct.
Sir.
Yes. CP values are known, right? All the CP values are known. Calorific value of fuel, it is known because it's some like you are using some fuel which is generally very well controlled. Like the aviation fuel is typically around like somewhat like similar to kerosene. What about T03? Now only two parameters are left, right? Combustion efficiency is also known. Typically, it is taken around 0.98 or something. So it will be known for normal calculations based on combustion chamber design. So only unknowns are T03 and F. So which one is actually unknown and which one is known?
So
Among F or
T03 is the unknown. F is controlled, right?
not really. T03 is known. Why T03 is known?
It is
The
a
plate
material
temperature.
property.
It is based on the maximum temperature in the cycle, right? Material property, correct. So it is equal to you want to keep it equal to the optimum value, which is the maximum value that can be sustained by the turbine blade. And accordingly, F can be calculated from here. Obviously, for more complex situations, F is varied. So during intake, during takeoff, during landing. But these are for all normal operation like cruise operation or In these cases, for industrial turbines, normal, like at full throttle, say at normal operation, not at partial throttle, where you can reduce the work output by reducing the amount of fuel flooded. Okay. So this is how we need to take into account all the effects. I will show you in the next class how to take this into account using computer programs. Okay, means I will show you some, like, what are the changes that is happening, how much decrease in efficiency and work output happens, and there is significant change. So we have seen very large efficiency, 60% like this, but actually we will see that we are just obtain 30-40%, something like this. Okay. So you should be able to take into account all of this in your calculation. I will send you also a problem sheet, 3-4 problems to tonight, or when is the weekend? Tomorrow is weekend, right? Saturday, yes. Hopefully tomorrow I don't have anything, so I will send you. Yeah, yeah, tomorrow no seminars, I guess. So that's how we need to account for. Okay, so you should be able to solve this type of problems, and don't go with the solved problems. Means you can look at the problems, take the problems questions from the book of Ganeshan, okay, but don't solve in the way they have solved, because they have taken a lot of approximation. So you look at the problems that I sent to you, or if you want to look at more problems, you look at a few problems from the book by El Sayyad Ahmed. You cannot cover the entire book; it's a very large book, but at least 1 or 2 problems you can check from there. So because we are considering lot of, means all the other effects. Okay, many of these are not taken into account. For example, this calculation is done in a much more simplistic way in the book by Ganeshan, but this is more accurate, and we will do the more accurate calculation instead of. So some books may say that this is just equal to CPG T03 minus T02 by F into QCV. Okay, instead of taking this 1 plus F and here CPA. So we will not do like that. So let us move on, and a couple of more things need to be discussed before finishing this entire part of this part of the course. Okay, so there are two important parameters for quantifying the performance of gas turbines. Okay, so what are these parameters? One is specific fuel. So few parameters we have already seen: thermal efficiency of the cycle, but we will define it again now based on the new information that we have studied. Previously, we have defined some thermal efficiency for the ideal cycle and specific work output. So another very important parameter is the specific fuel consumption. Okay, so it is defined as the mass flow rate of fuel per unit power output. Okay, so you want to develop an engine which generates, engine means in this case I am telling about gas turbine engines. Okay, you want to develop a gas turbine which generates 100 kilowatt of power, and you want to run it for certain time. So you want to know how much fuel will be required. Okay, so per unit power, if you know the fuel consumption, then for whether if you design for 100 kilowatt or 200 kilowatt, you can accordingly scale the fuel consumption rate. So mass flow rate of fuel, which is kg per second, per unit power output, which is say kilojoule. Okay, kg per second per kilojoule. Okay, we'll come to the unit later. So this is written as SFC, specific fuel consumption, and this is equal to, so mass flow rate of fuel, which is m dot f. Okay, and power output, unit power output, sorry, not unit work output. Unit power output was kilowatt, not kilojoule. Okay, so power output is kilowatt. Okay, so mass flow rate of fuel m dot f by capital W net. Okay, overall power output, net power output. Now, if you divide by the mass flow rate of air, so you are left with F, which is the fuel air ratio, and in the bottom you get the amount of work per unit mass flow rate of air, which is small w net. Okay, so F by small w net. So F is what is the unit of F?
Unitless.
It is unitless. And W net is kilojoule per kg. Okay. Work per unit mass. Okay. So the overall unit for this is kg per kilojoule. Okay. So unit is kg per kilojoule. So it can be written as kg per kilowatt second. Why I'm writing like this? Because I want to convert it to kg per kilowatt hour. For practical purpose, this is calculated as kg per kilowatt hour. So this kilojoule we will write as, you can write as kilowatt second, and then we can multiply by 3600 to get the value in terms of kg per kilowatt hour. I will show you in a problem in the next class. So I don't think we have sufficient time today. So 3600 F by W net kg per kilowatt hour. Why kilowatt hour? Because per hour it is much easier to understand in practical purpose. So I want to run an engine of 100 kilowatt. I want to know what is the fuel consumption per hour. Okay, if I tell per hour, then it much easier for me to calculate the overall. So my engine will run for, my flight will run for 10 hours. What is the amount of fuel required? If I have it in per second, that's also fine, but we have to do some more calculation. So intuitively, per hour is much more easily understood. That's why it is, for practical purpose, it is written like that, although it's the same information. So this is what I was saying. So this is equal to basically m dot f by capital W net. Okay. If you cancel m dot f from the denominator and numerator, you get m dot, so f by small w net. The other important parameter, okay, two parameters I say, performance parameter, is the cycle efficiency. This is the actual cycle, overall thermal efficiency of the cycle. Overall efficiency of the cycle is equal to the net work output W net divided by the calorific value of the fuel. So it considers all the losses that are occurring. Okay. So net work output by the calorific value of the fuel. Calorific value of the fuel means of the fuel that is injected. So the mass of fuel injected per unit mass flow rate of air is F, and multiplied by calorific value per kg of fuel, QCV. So this gives us the calorific value of the fuel actually injected, F into QCV. So eta is equal to W net by F into QCV, and from this equation we can see that F by W net is equal to SFC. Okay, so W net by F is equal to 1 by SFC. So eta is equal to 1 by QCV into SFC. Okay, so these are all related. Obviously, it will be related, right? Because specific fuel consumption is related to efficiency. More efficiency means less fuel consumption. More fuel consumption means less efficiency. So they are related. Questions? Let us look at a problem. So I am just showing an example problem which takes into account all these different aspects, all the variations, and this will give you an idea about how to tackle similar problems. Okay, you can practice similar problems or solve similar problems. You can take up any problem from the book by L. Sayadame or Ganeshan's book also, but you solve it in this way, not in the way that they have shown. Your answer will be slightly different from their answer. So let us consider a case. It's actually longish problem, but let me see. I would like to finish it today, or we'll quickly go through it and then you can take a look at it later on. Because if I just start it and complete only halfway through it, in the next class again I have to start from the beginning. So an industrial gas turbine has two turbines, one of which powers the compressor and the second one is used for powering. So we will keep this open. So let me just, instead of reading, I will just explain. So there is a single compressor, and it is one turbine is exclusively running the compressor. Okay, one of which powers the compressor, and the second one is known as known as a free turbine. It does not, means the work output is not used. Any part of the work output is not used for compressor running the compressor. The entire work of the free turbine is used for running the external generator. So the net power output comes from the second turbine, and the first turbine is only there to run the compressor. Okay, so one turbine only for running the compressor, second turbine only for generating the power. This is known as a two-spool gas turbine. Two-spool because there are two shafts basically. One is the outer shaft on which the compressor and turbine high pressure turbine is mounted, and one is the inner shaft, concentric shaft on which the other turbine is mounted. The advantage of this type of design is that the two shafts can rotate at different speeds. Okay, so depending on your requirement, because the generator will require the turbine to rotate at a certain speed, but you want your compressor maybe to rotate at another speed. So for a two-spool design, although the cost will increase, but you can have different rotational speed. Another advantage is that the free turbine, what will be the density of the gas as compared to the first turbine? So high pressure, this is known as high pressure turbine, and second one is known as low pressure turbine. So what will be the density of gas in the low pressure turbine as compared to the high pressure turbine? Low pressure turbine will have a much lower density of gas because the pressure is low. So specific volume will be higher. As a result, for the same mass flow rate occurring in both the turbines, the length of the blades will be higher. This we have already discussed. Is it clear? Why the length of the blades will be higher in the second turbine?
Yes, sir.
Yes, because you need more cross-sectional area. Because the length of the blades are higher, if you rotate them at the same speed as the first turbine, okay, so this second turbine is actually limiting the design because you want the so your stresses are dependent on the length of the blade and the tip velocity also. Tip velocity is very high, right? If the length of the blade is larger, the tip is rotating at a higher. If the angular velocity is same, the linear velocity is higher, right? So as a result, if you rotate both the turbines at the same speed, the first turbine will have to be rotated at a less optimum speed, at a lower speed, because the second turbine controls the design. But if the second turbine is free, you can manage it to rotate at a lower angular speed, lower rotational speed, so that it is also within design limit, and the first turbine can be rotated at a higher angular speed because its blade lengths are smaller, so the stresses generated are smaller, so you can rotate it at a higher speed. Okay. So that's the advantage of a two-spool design. Obviously, it is more complicated, so cost will be higher for this type of design. And then there is a combustion chamber between the compressor and the turbine. Okay, and the exhaust gases from the first turbine goes into the second turbine and goes out from the second turbine. Okay, so some parameters are known. Okay, typical. This is like a real life scenario. So realistically, what will be known is given here. Okay, like a design problem. So atmospheric conditions will be known, ambient conditions. This is an industrial turbine. So the inlet pressure is P, ambient pressure is PA, which is 101.3 kilopascal, and ambient temperature is 15 degrees centigrade, 288 Kelvin. The compressor pressure ratio is 9. Maximum temperature in the cycle is 1380 Kelvin. And the efficiencies are known. Compressor efficiency, all these are isentropic efficiency because nothing is mentioned. If nothing is mentioned, it means that we will be using isentropic efficiency. If it is polytropic efficiency, it should be specifically mentioned in the problem. So isentropic efficiency of the compressor is 0.87. The combustion efficiency is 0.99. The turbine efficiency, so ETRT for the first turbine is 0.89, and for the free turbine FT is also 0.89. Nothing is mentioned about the about the transmission efficiency. We will assume that it's 100%. And calorific value of the fuel is 43 megajoule per kg, 43,000 kilojoule per kg. Delivery pressure of the free turbine. Okay. So this is what is delivery pressure of the free turbine. This is the outlet pressure from the free turbine. This is mentioned as 120 kilopascal. If it is not mentioned, what will be the pressure that we will take? If this line was not there, what would have been the pressure at 0.5 point?
Sir, it would be 100 atmospheric only, just above that.
Yes, it will be atmospheric pressure only because it will be directly releasing to the atmosphere. Okay. Here it is higher because maybe there is something attached downstream. So maybe there are because it's an industrial gas turbine. Sometimes what you like exhaust gas after treatment devices are there, which will reduce the pollutants if any pollutants are there. So that will lead to certain pressure drop. So if that, so ultimately the final outlet pressure will be equal to atmospheric pressure. If certain devices are there, here the pressure will have to be higher. We want the pressure here to be as low as possible so that we get the maximum work output, right? Larger the pressure difference in the turbine, you get more the work output. So we want to calculate the performance parameters. The performance parameters: net specific power output from this turbine, the efficiency of the turbine, means the entire cycle, and specific fuel consumption. So these three are the generally the performance parameter. Also, you want to calculate the fuel air ratio. Anyway, which will be required as the intermediate step, but we also want to calculate the how much fuel. Specific fuel consumption anyway we are calculating, but we also want to calculate the fuel air ratio required. Okay. So let us take a look at this problem. Only 10 minutes are left, but we will go quickly and then you can try to solve on your own. If any doubts are there, we will discuss in the next class. So inlet condition. So what I will do is I will keep the data here, okay, and later we will keep the diagram. So inlet condition, generally we will say, so we will solve. Remember, we will solve using stagnation properties. So T01 and P01. Then after compressor T02, P03, T02, P02. After combustion chamber T03, P03. After the high pressure turbine, it is T04, P04. And after the free turbine, it is T05 and P05. Okay. And the cycle looks like this. It's a real cycle. So the actual compression process goes from 01 to 02 non-isentropically instead of going from 01 to 02s. Okay. Then the combustion process. So now there was no mention of any pressure losses. So we will assume that there are no pressure losses. Okay. So from 02 to 03 is the constant pressure heat addition in the combustion chamber. And then from 03 to 04 is the expansion in the high pressure turbine, which is also non-isentropic. And from 04 to 05, expansion in the low pressure free turbine. Okay. What is the error in this diagram? There is an error in this diagram.
As
Yes.
P05 pressure should be at 120 kilopascal.
Correct. Good. So I have wrongly drawn it like this. So I have mentioned it here. P05 should be greater than P01. These are not same pressure lines. It should be higher than this. Okay. So please take into consideration. So let us, so solving this type of problems is actually easy, although it is the longest problem, but the process is not difficult. If you understand everything and if you can draw the cycle, you just have to go step by step, starting from 01 point, then 02, 03, 04, 05. Once you get all the temperature values, you can calculate all the parameters. Basically, our task becomes to find out all the temperature values, because all the energy changes, enthalpy changes, other things are in terms of Cp into the temperature change. So that is our task, right? So given ambient condition is PA 101.3 kP and TA 288 Kelvin. Okay. So at the inlet, the velocity will be negligible because it's an industrial gas turbine. So the stagnation pressure will also be equal to ambient pressure. So 101.3 kilopascal. Okay. And T01 will be 288 Kelvin. So P01, T01 is known. So for the compressor now, we want to find out T02. And all of you know how to do this. So just let me quickly go through it. So compressor pressure ratio is given as, the data also there. Compressor pressure ratio is given as 9. Okay. So T02s by T01 is P02 by P01. For this isentropic process from 01 to 02s, T02s by T01 is P02 by P01 to the power gamma of air. Remember, now we have to use defined gammas because it's a real cycle. So for this part, it is gamma of air. Gamma of air, even if it is not mentioned, we have to use like this. Okay. Gamma of air minus 1 by gamma of air, gamma A minus 1 by gamma A. So this value comes out to be 1.8734. Gamma of A I have taken equal to 1.4. Obviously, I have taken means it is the value. And CPA of A is 1.005 kilojoule per kg Kelvin. This will be required later. Okay. So from this, because T01 is 288 Kelvin, we find T02S, which is 539.5519 Kelvin. Remember, I had said previously, don't memorize any of those relations that we have derived. We have to go step by step. We don't need to remember those relations. Actually, we should not remember. Like if you use directly that relation and copy paste and put the result, I will not give you marks. So you have to derive, go step by step and solve the actual problem to show your understanding, instead of using those as formula. Anyway, for real problems you cannot do, but for ideal problems you could have done like that, but it is not the correct approach. So once you derive to T02S from the definition of compressor efficiency is defined as T02S minus T01 by T02 minus T01. Okay. So it is given as, what was the value? 0.87. So you can put 0.87, T01 and T02S are already known. So only unknown is T02. You can calculate T02. It comes out to be 577.1401 Kelvin. So this point is known. What about T03? It is already given, maximum temperature, 1380 Kelvin. So it is also known. What about the pressure here? This is also known, because the inlet pressure is 101.3 kPa. Pressure at 02, P02 will be compression ratio into P01. So 9 into 1.01, 101.3 kPa, right? So P03 is also equal to P02. So P03 is equal to P02 equal to compression ratio RC into P01. So this comes out. So this is 9 into 101.3 kPa. So this is equal to 911.7 kPa. Okay, we are assuming that there are no pressure losses. So from the combustion chamber now, we want to calculate the fuel air ratio, because without calculating that, we cannot find out the work output of the turbine. Because remember, the mass flow rate in the turbine is not 1, it is 1 plus F, because that extra amount of fuel is increasing the amount of fuel is increasing the mass flow rate. So our mass flow rate for the calculation of turbine work output is different from the mass flow rate for the calculation of the compressor work input. Okay. So energy balance in the combustion chamber, we have already done this. Okay. F is equal to, there is another mistake here. No. It's fine. So basically this was the equation. So eta V is equal to 1 plus F CPG T03 minus CPA T02 into F by QCV. This is what we are going to use. Okay. So you can do the energy balance also. So the change in energy is 1 plus F CPG T03 minus CPA T02. And this is equal to the combustion efficiency into calorific value into F. Okay. So from here, we will calculate. So here, everything is known. CPG is, what is CPG? 1.148. And T03 is the maximum temperature, which is 1380. CPA is 1.005. And T02 is 577, which we have already calculated, right? And eta V is given as 0.99. Combustion efficiency is given as 0.99. Calorific value is given as 43,000. And CPG again 1.148 and T03 known. So from this we get a fuel air ratio of 0.0245. Okay, so this is the answer to the first question, fuel air ratio. You can find the air fuel ratio from here. It will be 40, around 40 point something, right? So now for the high pressure turbine, we have to find, so 0.03 is known. T03 is 1380 Kelvin and P03 is also we have calculated. So what is unknown? Fuel mass means fuel air ratio is also known. Unknown is the, what is unknown here? Both T04 and P04 are unknown. So now if P04 is unknown, how will we calculate the value of T04? Generally P04 are known, and we calculate based on this isentropic relation, right? That P03 by P04 S to the power gamma by gamma minus, sorry, gamma, yes, to the power gamma minus 1 by gamma is T03 by T04. But it is unknown here, this pressure. So how will we calculate the pressure and temperature here? What extra relation, because both are unknown, temperature and pressure. So how to proceed at this point?
Like the work output will be equal to the work input to the compressor. So
Correct,
Max.
correct. Yes, good, correct. So work input to the compressor is equal to the work output from this turbine. So let us continue in the next class itself, okay? Because there is still some part left. You can take a look at the problem also, but we will continue in the next class and finish this and finish this topic and go on and start the jet engines part in the next class. Our time has run out. So I will take the attendance directly. Stop the recording.